Hello, this word is presented to the NetSys conference on the one-on workshop. The word is titled Molecular Communication Channel Modeling in FPGA Technology. The author from the Technical University of Berlin are Daniel, Matis, Va, Jorge, and Professor Falco Dresla. For the molecular communication scenario, when a point source releases molecules to reach the receiver, the released molecules will randomly move in all directions, and some of them will reach the destination, here depicted as an spherical receiver. This process of diffusion is analyzed macroscopically by the concentration level of the released molecules. Analytically, the concentration level will be given as a solution of the fixed second law. However, further analysis of this process can be derived when the diffusion is modeled as a linear time invariant system. Here the channel impulse response is derived as a solution to the fixed second law. The concentration level at the receiver can be obtained after convolution operation. When deriving the channel impulse response, the impact of channel effects like intersymbol interference and the channel frequency response can be more easily derived. In this direction, the work from Piero Boron and Ake Yildiz modeled the process of diffusion as a connection of linear systems for the emission, the diffusion, and the recession process. The emission process is modeled as a box containing molecules, those released through an aperture to the medium. After the molecules are free diffused through the medium, the recession process is conceived by means of chemical receptors. A molecule is captured at the receptor whenever it is not previously bounded to a particle. In this paper, this communication system is modeled through electric circuit for the transmitter and the receiver. The connection of current source, the capacitor, and the resistor conceive first-order system to model the emission rate controlled by the resistor value. Similar happens on the receiver, where diodes are also connected to model the recession ligand process here. A current may flow back to the source to characterize the case when molecules are released back because of the occupied receptor. However, the channel is modeled through a second-kind modified Bessel function, and not any electric circuit is provided here. In this work, we provide the implementation of the channel by approximating the Bessel function as a ratio of polynomials. Approximation is conceived for a digital system to be implemented in FPGA. We use direct 4-2 structures to implement the three processes: the transmission, the emissions, and the reception. We follow a two-step methodology to derive the transfer function on the digital domain through the bilinear transformation. Then we use the coefficients to implement the system in FPGA. The obtained coefficients are exhibited in this table. We modeled the channel with a third-order polynomial for the numerator and the denominator. The emitter and the receiver was obtained as a first-order polynomial. Results exhibit a well-correspondence for the channel attenuation between the FPGA implementation and the original system. In the channel, a closer approximation can be obtained whenever the order of the approximation function is increased. Here depicted is the case of the third-order polynomial. Conclusions: FPGA designs can effectively model diffusion processes with low computational resources. There is further potential to run multiple communication systems simultaneously, with each system modeling a different parameter setup. Extension to model complex multiple input and multiple output MIMO system might be also possible. Thanks for your attention. We are open to questions and further collaboration. You can have contact with us by this mail here on this slide. Thank you.